Hello everyone. I hope you can hear me. We'll wait for the hall clear. Yes, the sound is good. We'll try the other mic. I've got a new mic, so let's transition. Is it good? Is it too loud? It's perfect. Good. Nice. Okay, we start to have a good setup now. Hello everyone and welcome to my um, Tuesday stream. Um, so I wanted to try to get the affiliate uh, perks so I could keep my video longer on the website of Twitch, even though I transfer them to YouTube. And they want me to do more streams, so here I am today. We will continue the project I've started, and the goal is to go towards a 16-bit CPU. But right now, what we are trying to do is a simple multiplier. I call it a naive multiplier. You might find better implementation, but I just want people to understand the concept that we will tackle during all the process of making a CPU. We will start with a little introduction. So my name is Andrew. I'm currently a student doing my master degree at the university. It's an electrical engineering degree, master degree, but in fact, I'm more in the computer science part. I like very low level, so uh, how the CPU works, how accelerator works, write C, C++ code. But I also managed to program in higher levels such as Java, and I also work for at least 15 years in the marvelous world of web development. I was primarily a backend. I did both, but I was really more interested in backend. At some point in my career, I was fully backend and also did a lot of DevOps, so provisioning, server load balancing, caching with at the time Redis. Now Redis doesn't seem to have a good popularity, or in fact I don't know. I just saw some backslash around their change in their licensing. So now that can be a problem. But at some point I would say bored, but there wasn't any more um, uh, passion in what I was doing, and at some point I went to the what is it called, the faculty of engineering, and fall in love with all sort of project that they were doing there. A fully electrical a motorcycle. They did drone and competition. It was very interesting. So I see Rogelio. Yes, I found it sad that in Twitch there's not a lot of people talking about VHDL, and I wanted to in fact, in my like I said, I'm a student currently doing my master degree. I have I had the chance to teach as a tutor one of the class in the fourth term, sorry, of the back in computer science engineering, and the project is to make a what is called a PPU in the FPGA. So it's a processing picture processing unit. It's the kind of technology that the NES had at the time. And when I did the courses, I fell in love with the FPGA, but it wasn't that project. It's after that we saw that a lot of students were interested in the first project, where it was just a bunch of sensor, and the student was forced to find a project and for some reason, a lot of people didn't have any idea what to do. But when we said, hey, why we don't do something very interesting like a CPU or a GPU, something like that, my director at the time and still today proposed to make a PPU that is more accessible at this level. So I did an implementation myself. I won't show it in this stream because I don't want my student to um, pick it up and complete the project quickly. But this is why instead I'm doing a CPU. Okay, so that was the introduction. And now I will go back in what we have done so far. And I want to point out that there is a lot of things that is not clean. It's not on purpose. It's not perfect. The goal here is to uh, try some things and advance step by step, and look at the thought process behind how I approach this. There are people that would do it completely differently. Some people will have done it in 3 hours. I want to take my time here, so stay with me. So we'll go back in the project and look what we've done so far. And what I want to do is open the block design. And there's not much in the block design because the only thing we've done with it is make the UART work. So as I've shown before, we have our FPGA here. This is a ZenQ Z7-20, and that FPGA is special is that they are equipped with with CPUs. So there is 2 ARM core, and I can run pretty much what I want. I can run, for instance, Linux. I could run RTOSs, or I can run bare metal. Bare metal with meaning no OS running, only my code. My code is loaded during the bootstrap, and my application is the sole the sole system on the part of the FPGA. And you can see it if I double click in this ZenQ here. What you'll see is this connects to the FPGA fabric, and those 2 core here are Cortex A9, clock at 650 megahertz. It's not your typical 5 gigahertz you'll find on today's high-end computer, but they will do the job for what we want to do. We won't be making UIs and stuff like that. And those are 32-bit CPUs. They are connected to, I think, is to 512 megs of RAM, DDR3, and there are. If I go back to the device cam here, you can see that there is 2 HDMI connector. One is an input, the other one is the output. Those connector here are proprietary characters from Digilent. Digilent is the company that does this board. You can see the name here. So it's very strange that the board is oriented in that way, but the ZenQ is reverted. Okay, so Digilent is the company that made the board. ZenQ is the FPGA name that comes with ARM cores, and they are not usually, but at the beginning, Xilinx was the maker of that chip, but now Xilinx have been bought by AMD, and the Arty Z7 is the name of the card that Digilent made. You can have other cards at Digilent. This one is a Zibo. This is the card that we use in my university for the NES console. And as you can see, there are again 2 HDMI, basically the same connector but more PMOD. And this one has what is called a Arduino Shield, so we can connect Arduino Shield that we cannot on the Zibo Z7. So both of those cards have interesting feature. This one is, I think, is less expensive. I bought this with the Bluetooth connector P mode here, and a little OLED screen. I think it's like a 1 by 8 character long. I don't remember. I didn't really read the spec at the time when I bought this, but all of this system cost about $500 Canadian. But I think the Zibo, the lowest Zibo is in that range also. So it's not cheap, but it's not that expensive to try it out, and you can do a lot of stuff such as handling imagery and make I don't know, a project that will process images, audio, stuff like that. Okay. So coming back here, so if I close this, what you see, this is a so those blocks here are ones made by Xilinx. Xilinx provide us with those what is called IP, and they can all be configured or not depending on what we want to achieve. The minimal requirement to be able to talk to the CPUs are having those set up in that manner. And if you remember in the two first stream, what we did is making the UART work. So we need to use another IDE that is called Vitsys that will come to life very soon, I guess. Did it started? Sorry about that. So, oh, okay, it's starting. So I will open my workspace. I put it in C, working, and we go no software, and check folder. Okay, so there's a lot of stuff here. The only two that are important are this one, the Arty platform. This has been created when I generated what is called a hardware. Is it hardware wrapper or yeah, just the hardware. Okay, so when I created this block design, I had to create these do the synthesis. So the synthesis, it's a little bit like a compiler in the sense that it will try to define how many FPGA component I will need to make my project work. Then the implementation will take into account the FPGA and really say, okay, you need that many LUTs, that many flip-flops, that many block memory. I will try to start in that section of the FPGA and go along with it. And it might work, might not work, so it will restart this process. It's very transparent. We just run implementation, it will do its job. And at some point, if it works, it will complete the implementation, and then we generate the bit stream. So the bit stream, what we need to know about that is when I go back to the device here, the FPGA, the CPUs and the FPGA fabric doesn't keep any information. So when the CPU or the FPGA or the memory, the RAM is doesn't have any power, all the data it contains is lost. In fact, the FPGA itself, the fabric, is very, very similar to RAM. Okay, it's little tiny bits of RAM all over the place, interconnected with other stuff. And when we say, hey, I want to create a multiplier, I want to be able to receive those information, multiply them, return the value, what happens behind is it will activate a path containing all the information needed to do the calculation. And when I turn it off, everything is wiped. So the bit stream here represent it's the executable, we can say that, it compared to an executable, but for FPGAs, and define which switch to open in which order, and how for instance, lookup tables are filled, stuff like that. So we need a place to save this file, and usually it's on a Quad SPI flash module. There are other solutions. Now the FPGA is not connected because we won't be. I was hoping to make it work tonight, but I don't think we will get there. Maybe Friday or next week. So we only be doing simulation for now. But the goal here is when I will be ready to test on the FPGA, I will connect it through USB, and there's a switch that I say, okay, now you get your program through USB, or you get your program through the Quad SPI. Good. So if I go back here, that is the platform, and this will be pushed and used by our application. And that application for now is the Hello World here. We have made some changes. As of now, if we go to Hello World, we created a UART read. So it gives us the information that we have received. And what we do is while true, we listen to UART. At some point, we will receive something. Once it's done, we will write it back to the terminals, not the terminal, sorry, the UART port. So UART, I don't remember what the letter stands for, but it's very old. It's used by, if you remember back on the when I was really young, and still today in some capacity, the COM port. It's a port with I think it's 9 wires. So those ports are named COM, but in fact it's the protocol is RS-232, and they use in fact UART behind the scene. And what we do here is connect from our USB through the FPGA and reach the CPUs, our software where it runs. The CPU is running our software, and when we send data, it sends it back. Simple as that. So that was our two first stream. Today, last stream, what we did is starting to do a multiplier. So now we will go see the code. So we have started simply with a half adder. So this is basically usually the first like kind of project we do usually in FPGA. It's kind of the Hello World. So we have two inputs, A and B, that we want to add together. And if we go back to the writing, what we have is A plus B equal S, and we can have what is called a carry. So if we overflow, we want a carry to be equal to 1. Okay, and you remember, if I add 0 plus 0, we have 0, 0, 1, or 1 plus 0, those two equal 1. But if I do 1 plus 1, we have 0 here, carry 1, then those two here are zeros, we have 1. So S, the value is 0, 1, 1, 0, considering this truth table. And the C, the carry, is only true when both signals are true. So we've seen that this is an AND gate. So the AND truth table, this is a special one, is the exclusive OR, XOR in its simplified version. and this is can be compared to if I'm asking someone, let's say, did you eat your dinner and did it rain outside? So if someone did one of the two, it's always true, even though it can be true at the same time, it will be true. But this is more akin of like, hey, are you going to Montreal or Quebec tomorrow? And you cannot be at the same place at the same time. So you cannot be through both true. Going back here. Okay. Right. So this is what we see here. S is sum, C is carry, A, B are my signals that comes in the and I want those going back, going out. So we use the XOR command and the AND command to achieve that. So this will, in fact, make exactly what we've seen on my writings. So if I go here and look at my simulation, I've created what is called a TB half adder. And we try every single combination. And I thought about it. I found something. I found a linter from Sigazi. It's a company. It seems to be a well-known company in the industry, and they offer a educational license for their linter and some tools. And what it says is that my clock here is not needed, so we will remove this one. We will remove that also. Whoops, sorry. So now that we removed it, it will do exactly the same. So we start with SA and SB at 0. Then we wait for a certain period. We set A to 1. We wait for a period. The period is 10 nanoseconds. That represents a clock of 100 megahertz. We set SA at 0, SB at 1, and we repeat the process. And now what I do at the end is a wait. The wait here will tell my simulation that at some point you can like stop the simulation, everything is fine. So now I will set it as my top simulation. I think it's done, yes. And now I can run this. Good. Now we can use the these symbols that will give me a better visual of all of the time. When you open it, it's very so often very zoomed in. You can really see much. So this helps for that. And now we can go at the start and zoom with this, for instance. And what we see is exactly what I showed you. So when SA and SB is 0, SS and SC is 0 too. When one of the two signals are 1, SS is 1 and C is 0. Now, if both signals are 1, we have the SS that is 0, so we cannot be in Montreal and Quebec at the same time. But SC is 1 because it's an AND gate. We want that if both our signals are 1, we have a carry, so we overflow. Good. So we've seen that having a let's say half adder doesn't give us everything we need to make a real addition. Okay, so I won't go back on how we arrive at how to make an addition and chaining something else and a half adder to be able to do addition, but we did the code. So let's look at the code. So we go back to the source here and open now the full adder. And the full adder, what it is doing is, well, where is it? Here. Just a moment, please. Okay. Right. Donc, what I was saying is the full adder, what it is going to do is take into account that something might have overflow before itself. So you remember when I add my columns? So if I want to add something like 1 plus 1, 1 plus 1, what really happened is I have 0, 1, 0, 1, and there are something over there. Okay, this one I could ignore it, but for the sake of argument, I would keep it there. So these are carries. Those are my signal A, my signal B. So this is A1, A0, A1, A2, B0, B1, B2. And when I realize that there is a carry, I need to take it into account in the next add. Okay, so this will give me this full adder, receive A and B, will have a S, and the carry will go to the other full adder. A, B, C in, S, this is C out. Okay. Yo, Retro Gaming. Hey, Andra. Hey, hey. You back at you. Okay. So in order to be able to do the addition, what we do is add a single C in, like a carry in, and we have a carry out, and we will, after when we do the full adder, we will be able to chain them and use 16, 32, 64, the number of full adder we need. And so I won't go back to how it works again. We've seen it, and you can find a lot of documentation. But the way we can create a full adder is to use two half adder. One of the first one will be connected to A and B, and it's S. So the sum of that full adder will go to a signal that will be connected to the A of the second half adder. Let me draw this. It will be better. If look, I've heard that my sound is not that good with this new microphone. Is it better? Okay. Let me change this. Is this better now? Not that much. Is it because it's not enough loud enough, or is it broken? Like, okay, I will change it. Just a moment. I will change this. All right. Okay. I will just bring my other mic near. Is this better? Yeah. Okay. Sorry about that. Okay. Now what I want to say that the full adder will be comprised of two half adder. Half adder 0 and half adder 1. We have A and B coming in with C in. We will have a S and a carry out. So the first thing, we connect A and B to the first half adder, and the S of the first goes to the A of the second. So this is A, this is A, this is B, this is B. We connect the C in the B, like such. So what it represents is this wire here is A XOR B, and with when passing through this, we have a XOR B XOR Cn. Good. And the last thing we have to do is take this carry here and this carry here and put this in a OR gate. And this goes to the Cout. Perfect. Let's go back here. Yeah, okay. So now that our half adder is done, we needed some other, let's say, tools in order to do the multiplication. And one of the things we needed is a kind of shift register. And the shift register, what it does is it receives bits one by one and shift them. In our context here, it's not really what we want to do. What we want to do is first, we want to, and we will go to the drawing board, sorry. Okay. So when we multiply, what do we do in binary? Let's say I have four bits, 1 0 1 1 and 0 1 1 1. Okay, I want to multiply those two values. Okay, so what we can say is that this is labeled A and this is labeled B. Okay, and what we will do is we take this first number here, and if it's 1, if we multiply it by 1, we have 1. By 1, we have 1. By 0, we have 0. By 1, we have 1. So in fact, if I have a 1, I can copy all of this right below here. So this is what I would do. 1 1 0 1. Okay, now if I go that way, what will happen? So we will need to fill a 0 here, and if it's a 1, we will recopy again all those digits, okay, or all those bits. So 1 1 0 1. Then again we have a 1. So what we do, we have two number to our right. So we put our two zeros and then we recopied A. So what you can see is, in fact, there is a kind of pushing some data from that perspective and copying A. So it's always A with 0 to n zeros. Okay. And now if we have a 0, we can just ignore, because we will put a bunch of 0 here, and adding zeros doesn't do anything. Okay. So what we want after that, we want to make sure that all of those values are added together. So 1 0 1 1 1 1 1 0 0 1. And as you can see, I have 7 numbers for 8 at the start. I think if we do all ones, let's do this. I don't recall. So it's 1 1 1 1 1 1 1 1 1 2 3 1 2 3 4 5 6 7 8. Yeah, I think the maximum value will be twice as many bits as needed, because we will have here 1 0, so 0 1 0 1 1 1 0 1 1 1 0 1. So 1 2 3 4 5 6 7 8. Yeah. So the number of bits, the maximum number of bits we can have for a n by n multiplier is 2n. Perfect. So now I will need two devices, two entities that will have different jobs. The first one will generate that shifting. Okay, so it will receive a data of 8-bit. We have a load signal that would say, okay, when this is equal to 1, I want you to take those 8 bits and put them in a register. A register is something that will keep the data alive. It won't, if I change data at some point, the register inside my entity will keep the value it had unless the load is 1. And then we will have another signal that will called maybe compute. And when this is set to 1, there is a clock signal here at each rising edge. So when the clock is going from 0 to 1, then we will shift in the register. So the register will be 16 bits. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we fill the 8 first, and for every clock we move those value up. We add a 0 to the right, so it moves to the left. Okay. So, and we have a Q. Q will be the 16 bits of the register that go out, and this will in fact generate this process over here. But instead of 4-bit, it will be generated for a 8-bit going 8 shifts. Okay, just to make sure everything's fine. Perfect. The other one I will need is more akin of a serializer. So it's something that gets a data in parallel. So it will receive data 8-bit. So this, in fact, represent the A, and this will represent the B. Okay. And again, we have a load. And again, we have a compute. And again, we have a clock. And we have here a single Q that is 1-bit. And what it does, when I load my 8-bit my 8 bits, 1, 2, 3, 4, 5, 6, 7, 8, okay, it will output either, it will put the last bit here and then shift to the right, okay? So if we do the example of earlier, the first value, it will be a 1, then it will shift everything, it will become 0, 1, 1. The next clock, it returns 1 and then becomes 0, 1. Clock cycle, stands the 1, and now everything are zeros in that example, so it returns zeros. Okay, and what will happen is that when it is zeros, I will just tell don't do anything, because you don't have to add zeros. It won't be useful. Okay, so I started this last week, but I think I went a little I didn't do I think we can do better than what I started last week. I did some digging, and I'm not very satisfied about this little shift register. So we will create another one and go with a new one. So let's create this. We create in fact our two entity we want. The first one will be a kind like a shift register 16-bit, and what we want to say is that it fills from the left, not from the right. So we will add zeros from the least LSB, say least significant bit. Okay, so from LSB. Okay, it's the name is not very important. It's just that I want something that if we read it and look at the documentation, it will be self-explanatory. It might, I think most of the people that works in that industry doesn't really give long names, so it might not be what you are accustomed to, but I want to help you understand what we are doing. Oh, damn. And now Vivado crashed. and it's not the first time it did this. I think last week I tried some configuration with the multiplier, and I think in like 20 minutes it crashed like 3-4 times in a row, like in very short period of time. Okay, we are back. Let's go to okay, we will recreate our files. So create a file. It will be shift register 16-bit LSB. Okay, and another one, it will be the serializer. Well, 8-bit. And again, we send the LSB back. So serializer, it's like it will give us the values from the 8-bit, and each bit will be sent to our output, where the shift register starts with 8 bits, and we move those those 8 bits will be moved to the left, and that all 16 bits is sent back to the output. So okay, so now we finished. Now you'll see that this interface will be a little bit different. We will have our two files here. Now we can skip behavioral. In fact, I've seen some example on the internet. Often they keep behavioral, but what we are trying to do now is we want to do RTL. You can put it in caps or not, but RTL is register. I think is transfer level. What it means is that we will define all the steps that the data will go through, and behavioral, you can be a little more like if you were going to code in C. It's not really the same, but what I mean is that you can do some shortcut and let the synthesizer figuring out what you want to do, and sometimes it can be not as efficient as if you do it as a RTL. The problem with that is that RTL used to be a little bit more cumbersome. You need to do your register, your signals by yourself, where you might not really need it in behavioral. Good. So what we add here is data in of 8 bits. We have a load that is a single wire. We will have a clock. We will have a Q that is an output of 16 bits, and we have a we have compute that is an input, a single value. Let's put this. I like to have like my inputs, then clock and write enable, stuff like that, and then my outputs. It's not very that important, and we will have the same values here. So data 8-7-20. We will have a load, a compute. We will have a clock, and then we have the Q. That is an output, but a single bit now. Great. Okay, so let's press OK. I think everything is fine. So we will let it work. First of all, I wanted to talk about something real quick. I tried something like yesterday. It's been a long time since I learned that most of the people that works in the industry doesn't really use Vivado or Quartus from Intel directly. They have their sets of tools and software IDE, stuff like that, and will through Tickle script generate the Vivado project at the end, so they can test, simulate, do a lot of stuff out of this environment, and at the end they will bring all of this together and just run through code the generation of the bit stream and so forth. So it's possible that Friday or next week I will be doing a transfer but I will try to do it after completing the multiplier. So we will start over from there, explaining the environment, and then continue to our journey with the 16-bit CPU. Good. So now we have our shift register 16. No, this is not the, yes, this is the one. Okay. So this is the new one. And what we will do is remove this like this, and okay. So we see the code, and the chat is not annoying. 1 second. And I'm back. Okay. So what we did say is the shift register will receive a data of 8-bit, and will store this data into a 16-bit register when load is set to 1. Then when we start compute, so when we put compute at 1, then for every clock cycle, we will have the data being shifted to the left with a fill zero fill. So we put a 0 to the right, so all of the bits goes to the left. Okay. So to create that register, we will create a signal that will be called reg16 std logic vector 15 down to 0. Good. And what we will do is a process that will look the clock and load. So if, no, in fact, it's just clock. If the clock begin, if the clock is changing, do something. So this is what the process is. It's looking through its sensitivity list, and when something happens in that list of signals, it will do what is defined in this code, part of the code. Okay, so let's keep it simple for now. We will ignore the compute. We will ignore we will just like take the data when load is 1 at the rising edge. Okay, so if rising edge of the clock, so this will return true if the clock is rising, and load equal 1. So we have asserted the load signals. So we will set s reg16 will be equal to 1, 2, 3, 4, 5, 6, 7, 8. Concatenate with data. That's it. So what is happening here? Data is 8-bit. This is 8 zeros. We could have done x with 2 zeros here, and it's the same thing. And the % here signifies that we want to concatenate those two together. It's not like in C, where a single % means a bitwise AND operation. This is really not what is happening here. It's the concatenate operator for logic vectors. Okay, so now let's try just and at the not inside the process, but at any given time, we want that Q will be linked to the sreg16. So Q will always receive the info, is like connected to the sreg16, and sreg16 is either changing when load is 1 at the rising edge or is staying the same. So for now, compute and the compute doesn't do anything, and we don't have the process of shifting all those bits. So we will create a simulation, a test bench, while I take a sip of water. And I'm back. So like I said, I like to use TB and then the name of my entity to test. There is no ports. Simulation. TB, I think it is this one here. Okay, so let's save this. So I will copy. You should be I don't remember what is the word in English, but you should be accustomed to this part where I copy everything everywhere. This is one of the many things I don't like in VHDL, is that I need to repeat myself a lot of places. And so if I have to use, let's take the half adder for instance. It's a good example. The half adder here is used in the full adder, and it is used twice. So there is 2-port map, and we have also the test bench half adder. So if I were to realize that my half adder is not correct and I have to change it, what happens? I will change my entity in half adder. I will change the components in both full adder and the test bench. And if I change names, and when I do my port maps, I use the full. You can do either. You can do either this syntax or this syntax. So half adder port map, and then we have A B S A XOR B SC0. I could instantiate like this. There's no problem with that. And if you use that techniques, you will get a warning. And that warning is also relevant with the Sigazi. So I don't know if I pronounce it correctly. Sigazi is the company that provides tools for WillEnter, but gives other tools that are very expensive. I think it's what is the name? Let me look it up. IDE. Oh, maybe it's not that one. Is it Sigazi Studio? No, it's not that one I was talking about. Let me just look. Yeah, when your website has no pricing but request a demo or get in touch, it pretty much means. I think the company I'm talking about, I was PGA Dev ID. Okay. No, it's not that one. I was sure it was Sigazi. So what I'm talking about here is this company here. And what I'm using right now, the test I did by myself was a plugin for VS Code, and it gives us a lot of tools. And so I don't see the price here. No, that is not what I want to see. Manual, okay, but I found. I'm pretty sure it was Simplify. Oh, Synopsys. Okay, that was my mistake. So what I found and were quickly quickly discouraged is this company where you can even see your that is crazy. In fact, we will be doing this tonight, but we can see here those looks a lot like a state machine, finite state machine, so FSM, yeah. And they are very useful in the FPGA and IC design. So but this is like not free. Okay, I don't remember where I saw the prices, but I think it goes in like $19,000 per year, US. So it's not they if you are using this is because you know what you're doing. So you're not me with my master degree in process and not really working any FPGA job. So you know what you're doing. You have a team of engineers that are costing you a lot of money. So that 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 $19,000 is just like a rounding error at this point. So it's very it's not for mere mortals who work with like this little $500 boards, but when you have a $5,000 FPGA that connect an EPCI Express lane, not lane but port on your computer, it's another game. And I know I talked about it in previous stream, but one of the things you need to know also is that when you buy a $500 FPGA like this one, usually all the component inside the IPs that we see here in my block design here won't be long. They usually are free. Okay, I've like I said, I did a picture processing unit similar to a NES Nintendo console back in the 80s for a project in one of our terms, and there weren't any IP I wanted to use or needed to use that wasn't free, and that includes connecting a our PPU to the HDMI. So the HDMI, there are a lot of system video processing subsystem. There are a AXC stream connector there. There's interconnect also. There's a lot of things that need to be used, and all of that was free. But when you pay $5,000 for FPGA that you put in the computer, and as like 400 gigabytes um, uh, optic networking connectors, there might be a lot of those IP that you will have to pay again. So you pay for the card a really large amount of money. You pay IPs such as this one a lot of money, and again on top of that, software that costs a lot of money. So it's if you want to go in that direction, it's at a certain point you will need to go into either academic or in a company where they design stuff with these technology. So I hope I'm not discouraging you. I'm my goal here is to on the contrary motivate you to say, okay, I need to know these things and perform like that in that area to be able to get jobs in that area also. Okay. So going back to the register here, it's over there. Okay, so now that I've shift registered, the only thing we can test right now is the load data and make sure the Q changes with the value I have in the data. And if I change data without changing the load during multiple clock cycle, I shouldn't be having anything changing. Good. So let's have a process like, okay, you can name your process, CLK process, begin, and process, CLK process. And all of this, what we'll do is first we will have a signal, SCLK, STD logic, that it starts to 0. And right before the process start, we will connect SCLK to CLK. And here was a problem. Oh, yeah. it's in. Okay, yeah. I will then wait. How did I do that earlier? Oh yeah, it's because I need to point maps. Yeah. So UIT, we have a shift register 16-bit LSB port map, and we will have all of the signals we need. So data is data. Let's copy this. It will be quicker. Like this. Signal, 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 signal. This. No in, no in, no in, no in, no out. And let's remove this one. S. Yeah, good. We need our semicolon. So now we can connect. And let's not complexify anything. S load, S compute, S CLK, SQ, like so. So it will throw a warning, but who cares, right? All right. Water. Okay, I'm back. Okay, now that we have this, we can now make sure that SCLK will oscillate from 0 to 1 to 0, considering our 10 nanosecond period. So let's create a constant period of type time that is equal to 10 nanosecond. Oh, and it crashes because sure, when you have to stream, why would you want to crash, right? The demo gods. Okay. I'll probably look up like what are the messages in the logs, but I don't want to look it up right now. Okay. First bunch. We go to this one here. And what did we miss? Nothing. All right. So now we want, yes, we have the period here. We start SCLK to 0. And we could also start our S data to 0. So it's 8 bits. So 2 hexadecimals. Oh, I think it needs to be like that. The load will be equal to 1 to 0 at the start. Compute, we don't care. We won't be changing this, but we will still put a 0 there. And just to make sure everything is well aligned and coherent. We like coherency. Sorry. Okay. Now we need to wait for period divided by 2. Period in caps. Period divided by 2. So we wait half of a period. So in fact, when you have an oscillation, what you want is that the period is when you start from point A, go to point B, and then go back to point A. That is a period. So we pass half of our time at 0, half of our time at 1. And since we started with 0, we can make SCLK equal not SCLK, then switching to a 1. And when it's 1, it switches back to a 0. And it goes all round and round and round. Good. So now we are ready to test bench. Process. And now we will do some tests. So the first test we want to do is change the value of data and not asserting load and wait 2 or 3 cycle period and making sure that Q stays at 0, because don't forget that S data is equal to 0. We set S data here in the port map, so it goes to our here, this data here, that is used to fill the sreg. And the sreg, in fact, what we want to do is make sure this one is also set to 16 zeros, so 4 hexadecimals. Okay, so you see, if I wouldn't have seen this, the sreg would have been undefined, or it's either U or X, and it's not really a problem, but I don't really like to have undefined signals. I find them very dangerous. Okay, so we go here and set data equal to 5A. So 5A, what it does is it as data, sorry. So what it does is it's change 5 is 0 0 0 1 0 1, and A it's 1 0 1 0. So it's a pattern of alternating bits, and with like a syncopated alternating bit. So tuta tuta ta tuta tuta, like almost like a paradoodle. For those drummers who listen to this feed, this is what it looks like. So if I wait for I don't know, period times 2, and then as data I change it to A5, and then set load to 1, and wait for period, and then load to 0, wait for period, and then as data to 1 3, no, 42, come on, right, 42, and wait for, just wait. Okay, so, and what's the problem? S load, perfect. So what happened is, what's here the problem? Load, yeah, change it. Oh, I really don't like that. Sorry, it's Vitis is not that bad. In fact, I tried some other project in the side, and I figure how it where it's going, but Vivado, it's really a pain. It's really a pain. Okay, I probably make sure that next week we will be using other IDE and tackle how to use Tickle script to generate projects. In fact, I've heard that if you want to go to GitHub or Bitbucket, whatever Git services you want to use, the best way is not getting the entire Vedo project, is just getting the Tickle scripts that needs to reconstruct the project. Okay. So now we are ready to test our beautiful, simple setter, since it doesn't do anything more than just setting the value. There is no steps again to shift those values. So now we go here and make it a top simulation, right? And now we can run the simulation. So now it crashes. So last time I think we've saw this. So you remember that my GUI crashed, right? So if I close it, in fact I should see no Vivado process, right? If I go in a test manager, and we see visit this is for Vitsis, okay? So let's do this. All right. Okay. So if I go down here, I shouldn't find any Vivado process, right? And last week we didn't see one. So when the simulation crashed, we didn't have this Vivado here. Now, if I last week what I were doing was deleting the simulation point simulation.log, I think, and it worked fine. But I think if I just kill this and task, then start Vivado. Yeah, so if I start back Vivado, then run our project, and then run simulation, everything works fine. So last week, there weren't any Vivado process still working. So we had to go to the folder and delete the simulation.log while the Vivado was closed. So I closed Vivado. There weren't any thread running or process. Then when I deleted the file, everything worked back to normal. Now, it crashed earlier, but there were still a hidden process somewhere. And that process would have provided me, not provided, but would have prevented me to delete the simulation. But you don't see when you look at the top, you don't see any Vivado like this. So this is like the Vivado we are used to see, but now it's back in the hidden process. Okay, so now let's do this and go back at the start. We want to see, can I zoom this? Would be great, right? Okay, so if I do this, it will be, I think, enough. So you see that the Q here stays 0 as long as either S load is 0, but once S load is 1, we have a change in SQ at the rising edge of the clock. So here, right there is the rising edge of the clock, and load is at 1. So all our module does is copy this 8 bits with 8 zeros to the register of 16 bits that is connected to the SQ here. Okay, and now we see that we changed a 42 here, but never it is as the load is asserted. So for as long as load stays to 0, the clock can wiggle down and up all at once. The SQ will stay at the value A5. Great. Okay, so how do we now start the compute process to shift our we want to shift 8 times the 8 bits to the left. Okay, sorry, maybe you see it in the wrong the wrong side on the screen, but you understand what I mean. So you have all the numbers, the 8 zeros plus all the data that has been loaded, and I will put a 0 at the right hand, so all the data goes to the left. So how can we do this? So I want to approach this for this example, and I'm pretty sure there are simpler ways. Is we will, when we assert compute to 1, each clock cycle we will do that movement of adding a 0 to the right, so it moves to the left. So here we will say else if, yes, compute is 1, then, and I want to be sure that the rising edge is also true. So let's copy this here. And what we do is, so sreg 16 will be equal to it will take, so if we think about it, we have 16 bits. The last one will be lost forever. The 15 first will be shift. So what we do is sreg 16, we take from 14 down to 0. So we take the 15 first. Okay, don't forget that the 0 is, we count the 0 as a bit. So the 0th through the 14th, and we then have 15 bits. And we put the 1 at the start. So what this line does is exactly what we want to do, is shifting our it shifts to the left by adding a 0 at the right side. Okay, so let's try this. Let's make some tests. We go to the here. Oh, I think it's already, no, it's not open. Test bench shift register LSB. So now we, at that point here, we know that the value is still, I think it's A5. Okay, so what we want to do is add 0, so it will push to the left. So s compute receive 1, wait for period times 8 for 8 clocks. S compute receive 0, wait. Okay, so not that big of a deal. Let's try this. So we run simulation. Yes. So close the first simulation we did, then we run this simulation for the new stuff. Okay, so I can see already that it worked, because A500 is exactly what it looked like if we takes A5 and shifted 8 bits to the left. Okay, so pretty sure it worked well. Let's see either way. Let's zoom this here. Boom, 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 boom. Okay, so at that point here, I set my S compute to 1. And so at that clock cycle here, we have 1 for A. Okay, and it's just think about it. 5 is 0, 1 is 0, 1. If I add a 0, I will have 1 0 1 0 as my 4 bytes. It's an A. If I have A, it's 1 0 1 0, and if I have a 0 coming in, like the 5 gives me a 0, I will have 0 1 0 0. It's the value 4. Okay, and we can see all of those values change for all the rising edge whilst the compute is set to 1. And then when I hit my 8th period, I go back to a S compute to 0, and A5 stays into my register, my register. So great, it works. Now let's tackle our serializer. If it wants to work, I'm clicking and it doesn't do anything. Okay. Well, yes, I want to be in this. Why does it not working here? Yay! I'm so happy right now. Okay. Let's restart Vivado again. Yet again. Water. Well, that's fun. Okay, let's kill this. And task. Good. Let's make sure there are no Vivado process down here. Great. I can close this also. I don't need it anymore. And let's restart Vivado. Okay. We go in serializer here. Nice. I think we have to be very polite with Vivado. It's I like to say to my students when I do the classes for the PPU, and what I explain to my student is that Vivado, Vitis, all of those technology are in a quantum state. So when you do stuff, sometimes you say, hey, now my configuration, I want you to set this settings to that value. Okay? And you press apply. But for all other software you can find on the internet that is like at a certain level of quality, you expect that the apply button applied your settings. But Vivado is different. What Vivado it does is it gives the ability to Vivado to be in a quantum state as either it changed or not. And it's when it is the most important to you that Vivado will randomly set or not the applied config you did. So it's very, very cumbersome. Sometimes I had a lot of problem that I thought my code was wrong, but at some level it was a config that I had to reapply. One of the example I have very often is when you have here a wrapper, and when you do the HDL wrapper, there's a settings that says, do you let Vivado to figure out when it is important to update the wrapper? And very so often when there are bugs, it's the one thing I say, oh, did you recreate the HDL wrapper? No, retry it, and 80% of the time it's the problem. This is the problem. All right. So we will have basically the same logic here. Okay, so we have a signal that is the reg 1 bit. Let's see the logic. One moment, please. So I see we have FPGA Zealot. Hi there. How are you? Now, so we have this register, and let's go back to our shift register here, where we have a 16-bit that we will shift to the left. Now what we want to do is take the rightmost bit, so the LSB, and connect it to the Q, the output of my entity. Okay, so it's the logic would be pretty similar. Okay, so we will copy this here. We will change Q by only reg 0, so the LSB of my register, not my register, sorry, my oh no, yeah, okay, sorry, I'm going too fast right now. This is a 8-bit, and I want to connect my Q to the last bit here. So sreg 8, like such. Okay. Now if I want data to be set to sreg 8. All the data, there are no zeros added or moved. The only thing we need to do is set the reg to data. Okay. Now, if I want to do like a computation, like make my serializer send the bits one at a time, is I need to take the 7 most significant bits and move them to the end of my register, and at the front I put a 0. So making a 0 at the front is easy. Just say a 0, and s reg 8, it will be 7, the last bit, down to 1. Okay, so this will exactly do what we want, is shift all my bits by 1 and make sure that we connect the first LSB, so the least significant bit, to the output of my entity. So we can create a test bench again. I'm pretty sure you know by now that when we create an entity, we want to be sure it works properly, so we create a test bench. So create a file. It will be tb serializer 8-bit LSB. Okay, finished. Okay, yes. Good. Now we could recopy this here. It will be pretty similar. So in my TB here, and we will need our entity. No, it's the serializer output. Our entity here. Again, copy pasta. I think the people that created VHDL was sick of the concept of dry. They were like, let's make a language that will be as wet as possible. So like this, we will need a lot of signals, mainly all the same signals as these here, like this. The only difference is it's a logic like such. Good. Now serializer goes here. I think everything's fine. Now we set those values, and then so the test will be similar, but the only difference is that the bit that goes out will be only 1 bit at a time instead of a 16-bit, and the order of those values. So it's since it will be this, so we will have the first value will be a 1, then a 0, then a 1, then a 0, then a 0, then a 1, etc. Okay, so let's make this the top one. This one. Did I stop? Can you do? Let's see. What are the chances that my Vivado quantum superstate will be in failure or success? So if I run the simulation right now, will it fail or will it run? Oh, it runs. Great. That's perfect. Okay. So we need to zoom in. Oh, we have a little undefined over here. Let's make sure we will take into account that. Okay. So what we see is that the SQ in my serializer is not well defined. Okay. Let's just change it real quick. So here, let's set it to for 8 zeros. Don't forget, when I am in hexadecimal, each of those zeros are in fact 4-bit and 4 zeros. Okay, now let's go back to simulation. Run. Yes. Oh, there are errors. Step failed. Please check the TCL console. Okay. It says okay, so that is fun. It doesn't says much more about my problem except go there. So just to make sure I didn't put any error in there. So my signal is set to 0 here. Then if I have load to 1, I put my data into my register. And if my compute is 1, I shift. And then, okay, so I don't think there's an error here. Let's look at this problem, shall we? Okay. This. I think it was this one. Let's open this in code. And let's put this here. Okay. Syntax error near. Oh, I think oh, is it? It said I used this operator. So let's go back here. What was the file? Serializer 8-bit. I think I used the. Yeah, okay, yeah. So when you want to assign value to a signal, it's colon equal, not the arrow operator. So let's retry this, shall we? Yeah, thank you, Dalen exe execution. Okay, so now it works, I guess. Let's zoom in. Okay, so now, whoa. I really like this. Okay, so we have 5A here. Then at this point, the Q is set to the bit of is set to the value of the LSB of my register, even though I didn't compute yet. But the compute, what it does is it's the action of shifting. So if I go at this point, you'll see that my compute is set to 1. Okay, and now what I suppose can I see, wait a second, if I go here, I can see my reg here. Do I need to rerun this? Let's try. We will go, I think it's here. Go back and let's put I don't know, 50 millisecond, nanosecond. Play. Okay. I think it was too much, but it's not. Shouldn't be that long, I guess. It's more than 15 nanoseconds right now. Oh, I think I did a plus, yes, pause. Let's go back. Okay. Did I put enough? No. Let's microseconds. No, stop. Okay. Now let's do this and go at the start and zoom in. Okay. So, okay, yes, you can see here that we have the A5 value, and at the moment of setting our S compute here to 1, we have shifted to the why it's 2. So yes, okay, 5 it's 0 and 0 1. When I shift and 8 it's 1 0 1 0. So if I take the bit from 1 to 5, I will have 0 0 1 0. It's 2. Okay. Now I will have a 1 on the other side of that 4 bit. So if I shift it, I will have a 9, etc. So I think it's working. At the end, I should have a 0. Yes. So those bits seems to be accurate. I have a 1 here, 0 1 0 0 1 0 1. I have shifted all my values. Yes. So it works as intended. Great. Okay. So now if I go back, let's go back to the drawing board. Okay. So we remember that we have our A here that will serve to be shifted and added into an adder. And the B here, what it does is each bit here says if I have will give me either all zeros or A. Okay. And those are those two modules. This is the shift register. And this is the serializer. 1 second, please. Okay, so we will have our full adder here. We will have A and B here that are both 16 bits. Let's redraw this a little big. Let's take another page and we will take our times to put it very, very clean. So this is our full adder, 16-bit. We have A, that is 16-bit, B, that is 16-bit, and we have a Cin, that is 1-bit. But this will be set to 0. We won't be needing it for our multiplier. But at some point, maybe we will want this functionality. There is a place where it comes in handy. Now we have the sum in 16-bit, and we have a cout, carry out, and so this one will be probably sent back somewhere if needed, but it could be also just not connected. Okay, we could send back the flag of this the overflow, but we could also not send it. Okay, and okay, now we will have our this will be our serializer, and this will be our shift register. And let's move this a little bit because we will need something in the middle. Okay, so now what we want is we will take our value. So let's start with, for example, what we had earlier. This is, we know that there is a coming in and a B. We said that this will be B and this will be A. Don't confuse these with these. They are not the same. Okay. We could just for the drawing here say OP0 and OP1. But what we want to multiply are the A here, that to represent the value here, that in fact will get shifted, and B that get serialized. Okay. All right. So this gives us a shift on 16 bits. Okay. And this will give us a B ser or serialize. Sometimes you will see in documentation ser des. Ser is serialization. There is deserialization. It's akin of modem, that is modularization, demodularization. So it's the process of transforming from a certain concept to another one and back. Okay. So now what we want is when we start. So when we start the process of multiplying, we start at 0 and we will add either this, the A if the first B is 1, or we add 0, so we add nothing if it's 0. Okay. So what we will do is what is called a multiplexer. Okay, so this is called a multiplexer. Let's take another color here. Multiplexer. And this takes two inputs. This is in this example. So we will have this here, and we will have another input that is in fact 16 zeros. Okay, and this here is what is called a select. Okay, so this, if it's 0, it takes the port 0, and if it's 1, it takes the port 1 and output it as an output. So it goes right there. Okay, so you tell me, yeah, but you don't multiply anything. You don't have anything on the operand 0 of your full adder, right? When we start, when we do our first, we have another multiplexer that goes into here. It's at when we are at the step 0, so when we start the multiplication, we will have again all zeros here. So 16 zeros. Okay. And this will be connected to the output of the sum. Okay. So let's take let's think about this, shall we? Step when we want to multiply this value with this value. When we start, we will call it step 1. Let's write this in that color. Step, like step 1. Okay, step 0 is when you load everything. Step 1 is when you start the compute. Okay, so let's call this here OP mux O 0, and this one will be OP mux 1. Okay, So step 1, we will have this is the select. This one also is a select. So step 1, we opmux 0.select will be set to 0, and either in that example we will have a 1 here, so we will have that value out that will output from here, so we will have 0 0 0 0 16 12 times and 1 0 1 1 that goes on in there. This is 0. We will have at that point sum equals 1 0 1 1. Step 2, and up to step 8, we will have op mux 0.select set to 1, because now we will take the sum. If we add 0 here, so 0 plus 0, sum will be 0, then we will put 0 back here, and it will be okay to put a 0 here from our sum. Okay, and then sum in that example will be equal to 1 0 1 1 plus 1 0 1 1 0 1 0 0 0 0 1. It will equal this. It goes back here. It's again select 1, so this goes back here. Now we have a 1 here, so we will receive here a 1 0 1 1 0 0. It will be added to this value, so 0 0 1 1 0 1. It's 1 0 1 1 0 0 1. Sorry, it's a little bit cramped. Let's rewrite this. 1 0 1 1 0 0 1. All right, and since all other all other b's in that example here are all zeros, so at the end of the process we will have that value as the multiplication of those two. And just for the sake of happiness, let's compute this one. So 1 plus 4 plus 8 plus 16 32 64. So we have 72 76 77. Is it right? And we have here, that is B, so it's 11. This is 7. Yeah, that's exactly it. 77. Woohoo! I was afraid. All right. So now what we need to do is we can create those, like we can create the multiplexer, and we will create signals to interconnect all of these, but we realize that when we do a computation, we will also need something called a controller. So if I go back here, I will need a controller, and that controller will make sure that this signal here, this signal here is the right one, considering to which step we are in the process of the multiplication. Okay, so let's do this. Do I have something else? In the controller will also feed A and B. In the simulation we will do either today or Friday, we will probably just set some value, but once the controller is done, the next step will be to create a AXI module that will connect our controller to our CPU. And now that will be fun, because at that point we will be able to, from a UART terminal, so a COM terminal, we'll be able to send values to the CPUs that will send it to our multiplier, that will return to the CPU the answer, that will return the value to the terminal. And now we will have a quite simple system. Okay, great. I almost turned off my iPad. Sorry, I'm back here. Okay, good. So let's make the multiplexer. Go here, plus, create file, plexer. It's a, are they both? Okay, no, there, yes. Both of these multiplexer will have an output, have two 16-bit output. 2 by 16 bit. Okay. And like, okay, let's do this like this. Finish. We will need a in 1, like in 0, in 1. Those are 16 bits. So we are at 15 here. And we have a cell select. The term select, I think it's a keyword, so we can take it. And we will have Q, that is out 15. We are in the clear. Great. So, okay. Multiplexer. And so I think it's very straightforward. What we need to do is process in 0, in 1, begin and process. And if no, it's cell works, we want to see if cell change. So if cell equals 0, then you receive in 0, else you receive in 1. And if. Okay, so I think it's great. Let's create a test bench, shall we? Simulation. Create a file. EB multiplexer 2 by 16 bit. Okay. Finish. Yes, yes. Multiplexer. So it's pretty easy. We will again copy this component. We will need signals. I think we can use multi-select, right? Oh, yeah. Like this. Signal S control. Okay, we cannot. It's not that good. Okay. So like such, and we need a semicolon here. We don't need any clock. Just a constant period time 10 nanosecond seconds. Good. So now we process, begin, end process. So let's say this will be equal to beef. This will be equal to dead. And with a small x, I don't know if it changed anything. Okay, so let's just toggle those two. Oh, let's put the second 0. So in fact, at the start, it will be beef. So wait for period. SL will be 1. And don't forget to create our component. Otherwise, it will be quite useless. In 0, S in 1, SL, SQ. All right. Okay, so at that point, now the output will be dead. So let's change S in 0. Here. SL to 0, sorry. And wait for period. So now I should still keep seeing dead. But at the end, SN0 has no actual or default value. Oh, yeah, it's okay. It's okay. What is the problem? What is SN? Yeah, if I go here, is it done? Okay. It seems it has a problem. So if I change cell to 1 now, it should crash. Yay! Like I said earlier, I will be going to another IDE. So the problem is that my license is attached to a precise MAC address, and it's not on this computer, it's on my laptop, and it's not that good of a laptop. Okay. Simulation shift multiplexer. So I don't get it that expected architecture identifier. Oh yeah, of course. Is the architecture is here? Begin. Is there like a semicolon missing or something like that? Like or a sometimes I find myself in weird problems. SN. It says part in 1 in 0 as no actual or default. Okay. As no actual or default value. Why? I don't get that problem here. Okay, why is it? If I go back to my multiplexer here, okay. So I have in 0, in 1, SEL, and Q. And what I do is if cell is 0, in 0 goes to Q, in 1 goes to Q. And what I see over here is that, so it expects an architecture. Oh, yes, architecture is here. Behavior, is it this one? Architecture. Yeah. And okay, so I don't get why it says there is no architecture. We have this here. We don't have any ports. Then we have architecture behavioral of TB multiplexer is component our multiplexer. We port here. We have end component here. Then we have 4 signals that represent the connection here. We have a period. Begin. What is the problem? UUT the did I game port map. This is me at 10 o'clock in the evening, starting to feel the tiredness in my old self. Okay, great. So now what is going to happen? So at the start, S cell will be at 0, meaning we have S in 0 out, so we got beef. And when we set cell here at 1, we would get dead. Then when we set cell to 0, to back to 0, so no, okay. Right here, what I would like to do is change the SN0 to other values. So for example, let's say in 0 receive like lead, like such, and we wait. So in fact, we shouldn't see any change in the SN0. Yeah. Wait again. Why does Fedo hate me so much? Okay. So S in here. Got near the what? Can I use the X in? Yeah, I'm pretty sure I can do this. Let's try something else. 1, 2, 3. Let's say 1, 3, 3, 7. Why? What did I did wrong? Let's just look at like this one here. Yeah, I use X all around. So what's the matter with you? Okay, so now there's no problem. What are the messages? Let's clear this and retry this. X 11337. Okay. All right. Peak memory. Okay. I'm not sure what happened there, but again, sometimes it's just a pain. So now we wait for a period, so we shouldn't see, we still got dead at the output. Now if I change this to 0, now I should get lead. Okay, so it's a simple test, not that complicated, but let's do this. Wow. Set that stop. Okay, is it going to work now? Simulation will be let's stop this. Simulate.log cancels. Seems that the process still runs. Let's go here and task stop simulate restart Vivado. Arty Z7-20. Okay. Now we go in, we wait that the source gets filled. We go back. You just need to run simulation just to make sure the top one is the right one. Yeah. Run simulation. And we wait for some time. So we zoom. It seems that it worked properly. Okay. So at first, like I said, we add cell to 0. We add dead and beef. So in 0 is dead. In 1 is beef. So is it that? No, it's inverted. So in 0 is beef and in 1 is dead. So we have those two signals coming in our and we have a selection to 0 at the start. So we get beef. Now when we switch to 1, we get dead. And even though we change in 0 to lead, we still have dead because cell didn't change. So it goes up to the lead to the change in cell to 0, and now we have lead. So it works as intended. Great. So let's go back to this beauty. So this is done, and we created those two here. Now what we need to do is we could create like the controller, and the controller will instantiate these two here, 3 here, and we'll create those two here. Set zeros to the both and zeroth index of those multiplexer, and the controller will have A and B, and we'll look up this output at the end of the process, and the controller then needs to, oh sorry, the mic is very far away, sorry about that. So I repeat, the controller will instantiate all of this, will instantiate this, will set this to 0, connect all of the correct system, and at when all the multiplication is completed, what will happen is that this here will have the final sum, so the value of the multiplication at the end, and will output it as a product. All right. So let's create this module. Okay. So we go to source and we go here, create a file. We will call it a multiplier controller. Okay. So we will receive 2 8-bits. So A in bus 7, B in bus 7. We will have, let's say that we have a start, like multiply, like a single signal. We will have a clock, and the output is product. Output, it is 16 bits. And let's say that we have a done output. So when this is 1, it means that the product has been computed. We might not tackle, but explain more about interrupt at some point, and we could use this as an interrupt. So it will be ready if we use it. So okay, let's go back to the stream code layout, and let's open our multiplier controller. Okay, so let's first add a lot of component here. We will need almost all components we have. So we need the full adder 16. We will copy this and the multiplier. And this is now why it can be very, very heavy or annoying to like code all of this by hand. We could all do this in the the block design, but I want to go. There's some stuff I want to do uh, that it will be easier to explain in code. So we have the full header. We will need the oh yes, the 16.1. Yes, great. Let's go in the in this part here. It will be easier. So full header is here. We need the serializer. So this one. We will need the shift. This one. And we'll need the mux. Mux. Where is here? There. We need this here. Okay. Great. So there's a lot of signal we will need, and the first thing we will figure out is that load compute CLK, all of those signals will be handled by the controller, so we will need to synchronize all of this perfectly. So let's first of all create those signals. So signals S load, S compute, and we have already a input called clock, so we keep the this one, and those are ST logic. And we will need also, so this will be connected to this. B will be connected to this. So these, both of these will be connected to one of the two multiplexer. And after that, the full adder will receive Q. The B here will be the Q here. And the S will be feedback to the second multiplexer in 1. So we will be and in all in 0 have a 0. So we can create also a signal S zeros std logic vector down to 0 that is equal to 1 2 3 4. I don't know if I can. Could I put it constant? Yeah, I think it would be better. Okay, because I don't. In fact, it's routed to the ground, so those should just output 0. But in fact, it's not that simple. I guess the FPGA will just create a load table with 0, and that's it. Okay, so let's start by creating the shift register here. So shift register port map. So shift register data will be B. No, A. Oh. Will be A. There's no H in A. Then load is S load. S compute. I think I was really not aligned. Compute. Now we have, I think is the clock, CLK, and Q will go to a signal. So signal S this will be called the A. Let's call this A std logic vector 15 down to 0 and SA like such. Okay, and we will also need a signal SB that is std logic. Okay, is there a problem? SB. Oh, it's not saved. Yeah. Why? I know it's a logic vector U. Okay, so now we have the serializer. Sir, let's copy the name here. So the serializer port map will receive B, sload, scompute, circa SB. So now we have created these two here. Sorry. These two modules have been created, and this signal is SA, this signal is SB, ready to go to the DMUX here. So let's create the DMUX. Not the DMUX, the MUX, sorry. MUX 0. Let's copy the name, shall we? Multiplexer 1 by 1. Port map. So the in 0 will be S zeros, is a constant, and it's all zeros. And the in 1 is SA. The select is SB. And the output will go to, let's call this S shifted. STD logic vector 15 down to 0. Okay, so S shifted. Good. All right, now we can create, what is it? S0 is not declared. Oh yeah, there's a E, sorry. Okay, let's create the MUX1 multiplexer 2 by 16-bit port map S zeros. So now we want the output of the adder. So signal S sum std logic vector 15 down to 0. So we want the S sum here. Now the select, it will be a select we need to create and handle ourselves. Cell MUX1 std logic. So S, oh, damn. Why? I don't understand why it crashes that much. So we wait until it's ready. We are going there, going down over here. Yes, okay. So now we have cell MUX1, and the output will go into the A of the full adder. So signal S full adder A std logic vector 15 down to 0. So now this go here. And for the full adder 16-bit, I think I put the 16-bit right. No, I didn't. At first, I didn't put those marvelous bits. Okay, so A will be S full adder A. B will be S shifted. Then let's create a constant S0 std logic equal to 0 and connect C into S0. So there's no carry in. We will want to put the result as sum. That will be feedback into the multiplexer here. And the carry out, let's create a logic. So here, S carry out. S carry out. Good. Okay, so at this point, we've connected all of our modules together. There are some internal signals that we need to control, mainly the second multiplexer. So this multiplexer here, this one, we need to set it at 0 when we start the computation, and at the second clock we need to set it at 1. So like I explained earlier, the first time we multiply, we start at 0, the full adder as 0 accumulated, and we will add, if the output of the B is 1, we will take A and add it to 0, and at the next step sum will be that value A, and we want to add the A concatenated with the 0 if B is still 1. Okay, so it's a mouthful. I know it's a lot of interconnected information, but this is the job. Okay, so everything needs to be interconnected precisely and correctly. Okay, so now let me think. The next step would be to create a it's to create a, yeah, okay, before, like I said, this is to be handled internally. Sload and compute also needs to be handled correctly, and I guess this is pretty much everything we need to be sure they are correct. Okay, so now we need to go to the drawing board to create the what is called the state machine. Okay, I think we will have time to start. I think we finished with the start machine, and next stream Friday we will complete the code. All right, because it's already 10:24 and I'm starting to be exhausted. Okay, so we have states. Okay, give me 2 seconds, I'll be back. Okay, I'm back. Good. So we have as input, we have A and B. We have multiply. We have the clock. Those are inputs. And we have product and done as output. And signals that we need to handle correctly. Let me get the list here. So we have S-load, S-compute. We have S-cellmux. And I think this is all we need to, yeah, so these are all the signals that we will call control signals. Good. So when we start the system, we will have the initial initial state, and this initial state means that multiply is 0. And in fact, let's put it there. So we will call it M, and M equals 0. At the start of the process, we go to state, we would call it A, okay? And as far as we are concerned, as long as M equals 0, we stay in A. So A, what it means is we are like in a mode where we are waiting. Okay, the system is waiting to compute values. Okay, and the only way in order to make it multiply is when we have M equal 1. So B is the first step, and that step will be a load. So what do we do? Since A and B are already routed at the right place, so they are routed in the serializer and the shift register, when we set S load to 1, so S load will be equal to 1, we will the serializer and the shift register will be set to the value A and B. And then if we could say that that step can be either 0 or 1, it doesn't matter, we go to C. So C would be the first multiplication. The first step of multiplying by looking at the serializer output and getting the shifted value that is not shifted yet. Okay, so at that point, what we want is load will go back to 0, and we will set S cell mux to 0. You remember why? The reason why is that the full adder in its A input needs to be set to 0 at the first time we accumulate those shifts. Because what we want, in fact, is that if B is 0, we want A in the output of the sum. So we want to add 0 plus A. Okay? So then here, D, we have, again, M is 0 or 1. So we set cell mux to equal to 1. And there's not much things we need to do. At this point here, S compute is equal to 1. And it will stay 1 for each steps. Okay. So cell max equal 1. Then this D is the second step. And we need to do this second, third, fourth, fifth, sixth, seventh, and eighth. All right. So let's just say that this will be repeated 7 times. Okay, and the design I'm drawing here is not really a real compliant state machine, finite state machine, but the idea is that in the code we will probably create intermediary steps like a D, a E, a F, a J, etc. Okay, so for drawing I will just put a and in fact, yeah, sorry, this will be 6 times, because the 7th time we will go to a like a finalizer where we will set S compute to 0, and we will set the S sum in product, and we will set done to 1. Okay, and when it's done we go back to A. All right, what time is it? We could create the skeleton for this. Let's go back into the screencasts. Okay, so we will create a type that will be state, multiplier state is, and we will have waiting, loading, then we have step 1, step 2, step 3, sorry, step 3, step 4, step 5, step 6, step 7, final step, and I think this is pretty much it. Okay, and what we will do then is what we want to look at is the clock. So we create a process that will look up the clock. And now that we have this, what we want to do is yes, so it doesn't matter really about this. What we want to do is, if it is a rising edge, so if rising edge of the clock, then, and if, and we will have a case of our signal state, multiplier state, and we will start at waiting and state here like that. Is in case, and so sorry, I will, okay, sorry about that. Is it in case? I don't remember if I have a in case. Sorry about that. Again, let's go here. This is, yeah, it's okay. Okay, so I think it will tell me that I'll not I don't have any when anyway, so it doesn't like it. So when waiting, what do we do? And when loading, what do we do? When step 1, and we will have 2, 3, 4, 5, 6, 7 final. Is it final step? Yes, final step. 2, 3, 4, 5, 6, 7, final step. Good. Okay. So the only thing we need to do for tonight is just high level and set the right values at the right place. So when we are waiting, what we said in our design is S load must be 0. Did I? Okay, no, it's S load like that. When we have S compute will be 0 also. And S salmux we will keep it as well as a 0. Do we have anything else in our schema? I think it's all we have right now. Good. So now if multiply is 1, then state becomes loading. And if. Good. So when we are loading, we S load equal to 1. And then we state will be step 1. Step 1. Oh yeah, in step 1 we want S. So we keep in okay, so we put S load back to 0. We start S compute. And we let our set mux 1 at 0. But then we state step 2. Step 3, we will have S mux 1, so comes 1. State will be step 3. Step 4. Step 5. Step 6. Step 7. Final step. And in final step, what we do is we set okay, so we will have another signal that will be signal product. I don't think I've created it right. Yes. So it is a std logic vector 15 down to 0. And that will be instantiated to all zeros. Like so. Like such. And our S product here will receive S sum. And here we will have a product. Did I put a P, capitalized P here? Product here is receive S product. And we will have done receive 1. So back here, is it done or is yes? And wait, what we will do is something. I think I can do this. Done is 0 when state equal final step. I think this is something I can do. Is it other? I don't remember what or how I can say otherwise. It's PGL. Say it's set a output to a value when a state is Otherwise, okay. No, not that. Let's go back here. Oh yeah, I have an example in my notes, I think. No, not there. Not there either. Where are my examples? Okay, so what we can do is just, for now, done receive 1, and state goes back to waiting, and in waiting we will have done receive 0. All right, okay, good. So it will be the end of the stream. Next stream, what we will do is first create a test bench for this, make sure everything works as intended, and if we will probably have time. It depends on the time we need to debug. I think there is a problem with this setup, is that the serializer, I think, will be faster than the shift register, which means that we might need to create a delay of some sort. So we'll see if it works. If it works, I'm so happy. But if it doesn't work, we will probably need to create a delay between the compute we send to the serializer versus the switch register. So thank you guys to be there tonight, and we'll see you Friday.